Good evening, everyone. This is Celso Batalha, Astronomy 10, Evergreen Valley College, and today is Monday, July 16th. And let me get it started by sharing my screen with you. So I'm not sure if I had the microphone on before, but good evening, everyone. This is Celso Batalha, Evergreen Valley College, and microphone is on. I think everything is fine. And so let's see what's going on today. And we are in a summer session, and things go fast and at fast pace in summer. And as I always like to do, I like to go through our course and see what's going on and what we need to do. I just upload grades of our midterm number 2. And this week, we have reinitiated, in fact, a more in-depth study of star, pretty much going through the process of star formation and how stars evolve. That's going to be towards the end of this week. So 16 today, Tuesday and Wednesday with evolution, and then on the 19, the end process of stellar evolution, and then next week on July 23rd, which is Monday, then we have our midterm 3. So midterm 3 is focusing primarily on the sun, all the part related to stars. So the sun again, and then stars formation and stellar evolution. So that's where we are, and I have some students coming in. Anika, hey Anika, how are you doing? Haven't seen you around for a while. Okay, so I'm just initiating, showing where we are. Mandatory assessments beginning this week. We have a homework on stellar evolution, and there is a new discussion. So the discussion is somewhat simple. We are going to see today what's the core subject that follows stellar evolution, and that is the Hertzsprung-Russell diagram. And I will explain what that is, and then we go from there. But basically, when you look in the Hertzsprung-Russell diagram, there is a location that if you observe a star that happened to be in that location, you really don't know if the star is one that is evolving and becoming what we call red giant, or if the star is one that is forming. It's like you don't know if the star is a baby or if it is a senior, right? Not that senior is dying. I mean, it's getting close to the end of its evolutionary path. And the reason is when you observe them, their properties are similar as far as luminosity, temperature, gravity, and so we can't distinguish that. So, and the question is, and the discussion point is, what techniques should you envision in order to decide if the star is contracting, which means it's a young star, or if it is expanding, which means it's an old dying star. And so this discussion involves a little bit of the technicalities, and I would recommend you don't leave to the last moment. Like last week we had a discussion on exoplanets and the fact that the first group of exoplanets found, they were showing the characteristics of a Jupiter's type of planet, which means large and bloated with gas, as opposed to what we see in our solar system, which close to the stars we find terrestrial or rock type of planets and small. They are not big like Jupiter. So the point of discussion was, well, how can you form a planet Jupiter size with the characteristics of Jupiter, which we learn in planet formation, that can only be formed very far away and collecting, because it's far away, collecting in its majority a large percentage of volatiles and lighter elements. How can you find all these giant planets close to the stars? So what's going on? So I think the main point was to explain migration, the interaction of these Jupiter-sized planets when they are formed in the outer regions of their star system, and as they interact with the chunk of material still existing in the disks, like asteroids or whatnot, they lose angular momentum and then they migrate towards the central star. And then they eventually happen to be found closer to the star. So that was the point of discussion, and then I was certainly looking for the word migration. I was certainly looking for interaction with the disk. I was looking for some keywords in the discussion. So students who presented some results towards the end, I didn't have time to interact. So the best thing to do is to start your discussion as soon as possible, so that I can put my comments, and then you can improve, and then you can get better grades. So we are in the second week, the last 2 weeks of class. So we have this week and next week. Today is the day that if you have to make a decision to drop the class, just do it. You can withdraw the class with no record of a failing or D letter grade. But by tomorrow, if you are still in the class, you must receive a letter grade on your final exam. Okay, so I have to put that as a warning. I think I emailed the class. If not, I certainly do after this discussion. Okay, so Hertzsprung-Russell diagram is part of stellar evolution, and this is core. This is really core. So we have to learn what that means, or what this diagram represents, because it's going to be following us throughout the subject of this week, which is now when the stars are formed, tomorrow and the next day, how the stars evolve off a certain location in the HR diagram called main sequence, and then what happened when the stars achieve their evolutionary end, and what sort of a byproduct they release in the interstellar medium. So when you think about stars, we have this sense that the stars are there forever. Why? Because they live on a time span that is significantly larger than our own time span, or the span of our history. So think about our civilization is what, 10,000 years, 20,000 years, let's be generous. And 20,000 years is nothing when you compare with, for instance, the evolution of a star like our sun that takes 10 billion years, right? So it's pretty much a blink of an eye in a long time span. So yes, we look up to the sky and we see the stars apparently on and on and on and on the same, but they are changing. They are undergoing transformations, and with the tools that we are learning in this class, astronomers can identify these changes, and they can bring reasonable description on how they evolve. So certainly we can't stay observing stars for millions of years, but we can trace down an evolutionary story based on what we observe in different groups of stars. So evolutionary tracks, and I think you are seeing this here. By the way, sometimes I find myself talking to the walls because something was. Let me just check if everything is okay. If you guys are. Um,
You're fine. I can hear you.
okay. All right. Wonderful. That's what I want to hear. Um, an evolutionary track or a Hertzsprung-Russell HR diagram is one that relates, and that could be a valid question in midterm number 3. An HR diagram is one that relates in this vertical axis here. So these numbers where you're seeing in a logarithmic scale that goes 10 to minus 2 is 0.01, 1, which is 1. This is 100. This is 10,000. This is 100. No, this is a million. Sorry. So in this vertical axis, it gives luminosity. And what we saw last week, luminosity is the amount of energy the star sends out to space on a certain amount of time. But not only luminosity of the star, but the luminosity of the star as a function of the solar luminosity. For instance, this number 1 represents a star that has an output of energy that is equivalent to the sun's output of energy, right? And the star up here, let's say if you find a star up here at this level, 100 luminosity, it means that 100 times or 100 stars similar to the sun put together in a certain location, they will radiate enough energy to match the energy of 100 suns if we could, right? So that's what it means. So when you read the scale, so down here, 0.01 means the amount, the energy output of a star that happened to be in this region is equivalent to 100th, 1 over 100 of that output the sun is putting out. So which means the amount of energy is 100 times less than that of the sun. So that's how you read this vertical scale. Now, in the horizontal scale, it's kind of unusual because the numbers diminish as you go from left to right, as you can see here. So you start with 63,000, and then you go to 25,000, 10,000, 4,000, and then you go to a very low number. This number is surface temperature. It doesn't tell the temperature of the star in its very central part or in the middle of the star, but the average temperature of the gas that is radiating light we see. So we studied previously the sun has a region in its atmosphere called photosphere, which is the region where the actual light comes out. So when we see stars up in the sky, in the night sky, those dots of lights are lights coming out of the star photosphere. Okay. Now, this temperature scale, K stands for Kelvin. So Kelvin relates better with the Celsius scale, and is one that is 273, a number 273 plus whatever's Celsius temperature we are considering. And why astronomers use this scale instead of a Fahrenheit or Celsius, for instance? Well, the reason is this scale is called absolute scale and can be used to determine the amount of energy gas itself has. We are not studying physics here, but a astronomer that goes through the process of studying physics, she or he learned that a gas of a certain Kelvin temperature, that temperature is directly related to the amount of energy the molecules or the atoms or whatever that gas is made of carry in each one of its elements. Okay, so it's directly related. So for astronomers, if they want to kind of pin down the energetics of the star, it's easier to use this scale. So when we say a star is a 4,000 Kelvin star, an astronomer knows that star is relatively cool. It's a cool star. The sun is about 6,000 Kelvin. Is somewhere here in the scale, 6,000 Kelvin. A star like Sirius, for instance, Sirius, the brightest star in the sky, is one of 10,000 Kelvin. Okay, so the higher the temperature the star is, the bluer the star appears to our eyes. We also saw this effect in last week, right? The bluer, the hotter, and the redder, the cooler the star is. So a 4,000 Kelvin star is a cool star. Okay. So once you understand the scale and the axis, the vertical is energy, and the horizontal is surface temperature, sometimes it appears with spectral type, spectral classification, and then we have O stars, B, F, G, K, I forgot the A, so let's start again. O, B, A, F, K, M. I forgot the G, I can't believe it. Let's start again. O, B, A, F, G, K, M, and then you have the cooler end of brown dwarfs. So you can sometimes find this diagram in spectral type. But again, the spectral classification, OB, as we saw previously, relates to surface temperature. Okay. Now, what do we need to know about HR diagram? And for that, I would like to go to our NAAP Astronomy Labs. It's a great resource I use all the time, and I hope you are making good use of it. This is a display of HR diagrams right here. Again, you have the luminosity, see that? With the logarithm scale that I just explained. And right here in the horizontal axis, you have temperature. It goes from 40,000 all the way to about 2,000. Now, look at this locale in green. This locale in green is populated by a type of stars that are called dwarfs. Dwarfs. So we have red dwarfs, we have blue dwarfs, and they have a Roman letter identifying them as belonging to this locale, and the letter is the Roman number 5, or V. So dwarfs, V. So the classification of the stars are called dwarfs. They are also called main sequence. So in the HR diagram, these stars belong to what we call the main sequence. The main sequence. Okay. Now, to the right and up of the main sequence, and you read down here in the scale, see 5,000 to 2,300, we have a group of stars that are called red giants or giants. They are identified by a Roman letter 1, 2, 3, so 3, and they are giants. So these giants, as you can tell by their surface temperature, are in between 5,000 and 2,000. So they are cool stars. They are cool stars. I mean, we can't call 4,000 Kelvin cool because it would be vaporized so hot. But in comparison with other stars, they are cool stars. And because they are cool, they are red, and that's why the diagram depicts them with kind of a reddish coloration. Now, the stars on top of it, they are not in the main sequence, they are not red giants, but they occupy a range of luminosity that are very high. Look at this, 10,000, 100,000, a million times as luminous as the sun. These stars are called supergiants or blue giants, and they are labeled with the Roman number I or 1. So 1, the class 1 is for supergiants, class 3 for giants, class 5 for main sequence. And there are a class which doesn't appear here, but you might find in the literature, number 2, they are called bright giants. Bright giants. They lie between the main sequence and the giant groups. And they appear with the normal number, Roman number 2. So 1, 2, 3, 5, and no, I'm sorry, I said it wrong. So those between the main sequence and giants are number 4, subgiants. Subgiants. And the bright giants number 2 are between the supergiants and the red giants. So 1 somewhere here, 2 somewhere here, 3 and 4 somewhere here, and 5. Now to fill this group down here, and that is going to be the motive of our study tomorrow and Wednesday, you have the white dwarfs. So the white dwarfs are stars. They are very small. They are the size of our planet Earth. And because they are located in this region, and if you look down on the scale here, they are very hot. If you could see it, they would appear electric blue or blue, right? You don't see it because they are, as you can see in this scale, subliminous. So let's pull up this diagram and see if we can play around with it. So this is the star sun for comparison, and if you take this cursor and you bring to a locale of a main sequence, right? So let's say what a star in a main sequence that has a temperature, see if I can, so see, as I move it here, look at this scale right here. So the temperature keeps changing. See, if I move this scale laterally to the left, of course, the temperature scale grows, right? But the luminosity doesn't move much because I'm keeping in this level. So a star that happens to be located in this part of the HR diagram is one that has a low luminosity, but is very hot. Whereas, and that's what the star appears as far as size is concerned. See this little dot? That's what a star in this location of the HR diagram would look like. Small, blue, hot, and for all purposes, we couldn't see it. Now, one of those blue dwarfs in the main sequence that happen to be in this location, look at this. Their temperature is quite high. Their luminosity is quite high too. About 10 is about 10,000 as that of the sun. And then you can picture the size of this star, the comparison of it. Now, how about this supergiant we saw up here? So the supergiant up here would appear a tremendously large blue star with the luminosity that is 100,000 times as luminous as the sun. Now, if we probe another type of star called red supergiant, like Antares, the star, because its surface temperature is low, 4,000 Kelvin or so. Oops, where did I put my star? No, it's right here. The temperature is about 4,000 and so, but it is superluminous, 180,000 times the luminosity of the sun. Okay, so this HR diagram helps a lot to understand stellar evolution. So a star like our sun forms somewhere in this location of the HR diagram, and it goes through a process of contraction. It contracts, and as it contracts, the size diminishes because it's contracting because of gravity. And as we studied before in the solar formation, part of the gas that is contracting is driven by rotation to form the circumstellar disk. And then you ended up with a system consisting of a star plus a disk. Right? And then slowly the disk falls towards the star. And out of the remaining gas in the disk, everything else that is important for us in a star system, like planets and satellites and asteroids, comets, and all the junk we know that is out there in the solar system, all of that happened to be formed out of the material that exists in the disk. So the sun keeps contracting and then eventually switch a little bit and go to the main sequence. So the details of this evolutionary progression before arriving at the main sequence locale, and those stars are called PMS, pre-main sequence stars. So the pre-main sequence stars are young stars. They are in the process of contracting. They are kind of heating up, because as the gas forming these stars contract, it hits the gas, and the gas, the temperature internal goes up to the point that eventually the very central part of the star, we call the core, fusion reactions take place. As we saw when we studied the sun, the core of the sun has fusion reactions in which hydrogen atoms, 4 of them, fuse to form helium atoms. And in addition to one helium atom being formed, a surplus of energy is released that helps to keep the sun balanced. And we call that hydrostatic equilibrium, which is the equilibrium between the gravity force that try to contract the sun and the expanding forces that are associated with the gas and the release of that photons of those energy in the core. Now, so the pre-main sequence phase is one that the star is just contracting. Gravity is really contracting the star, bringing it to the point of having a central core that is hot enough to initiate fusion reactions. See that? So the fusion reactions in the core is not there since the very beginning of what we call a star. A pre-main sequence is a star, but it's not yet igniting its fusion reactions. So it doesn't produce yet enough energy to halt this contraction. So when the fusion reactions happen to be initiated, then enough energy comes out of the central part that halts the contraction. Does that make sense? So when the contraction halts and the fusion reactions is ignited, we call that phase the phase in which the star is a main sequence. So all the main sequence stars, all of those in this red line here, in fact 90% or more of the stars in the sky, they are main sequence stars. Not those we see out there, and that comes the extra credit. So today the classroom or this chat room will come with an extra credit, which I will show in a little bit. So if you go outside in the sky and you look at the stars in the sky, right, at night, so you see a bunch of stars there. What type of stars those are? I mean, we don't know if they are close to us. We don't know their size, their temperature. If we use technology, we might be able to answer some of these questions, but just by looking at them, we don't know. So what type of stars are those we see? The second question is, what type of stars are those next to us? Which means if you take a big scoop, like the Big Dipper, take the Big Dipper as a scoop, and you scoop out stars in our vicinity. So let's say go up to 20 light years, right? And then visit all the stars within the volume of 20 light years, or better saying the diameter of 20 light years. And visit all of them, and then make a sketch of their properties, put their properties in a scale. What type of stars those are? So the stars close to us are different from the stars we see in the sky, right? So that's the question. So the extra credit that you must answer and send it to me is what are the type of stars that are close to us? In other words, what is the average type of stars that is found in the galactic disk, in the disk of the Milky Way? We are a star system belonging to the disk of Milky Way. So if you take a scoop of stars, if we analyze an average group of stars within the disk, what type of stars are we going to see? That's one question you have to answer. The other question is, well, if you do a different exercise, and that is you go in a night sky with a nice telescope with a lot of information, and then you observe all the stars you can see with your unaided eye, which means all the bright stars out there, right? So you are probing not necessarily the type of stars close to us, but the stars that are bright. And as we saw in one of the past chapters, I think chapter 5, the one about light, I think chapter 5 or 6 maybe. The stars that are bright in the sky, they are bright because they could be luminous, and they are so luminous because they are huge, they are big. Right? And they are so big that you can see very far away. Does that make sense? So if a star is luminous, let's say hundreds of thousand times more luminous than the sun, those stars are huge. They are supergiant. So we can see them like beacons, like pharaohs, very far away, right? As opposed to the sun is a relatively small star, but it's in our backyard, so we can see it no matter what. Like if you light a match at night, because it's close to you, you can see well, but if somebody light a match miles away, you can't see it. Or maybe at night, a dark night, you might be able to see it. But anyways, so once the sun exhausts its fuel in the core, some changes happen, and the sun expands its surface into the giant phase, and that's what happened here. So the sun grows in size because now the fuel that was producing its energy during the main sequence phase, during this part of it here, is gone, right? The sun got exhausted. And because of that, some changes in the vicinity of the core will be affected. And I will discuss them tomorrow. So there's going to be a fusion of hydrogen on top of the core. The core now is inert and it's contracting. So there are a few changes in there, but the main point is the output of energy increases when that phase arrives. So the sun expands and then goes to some changes and becomes a red supergiant, and then eventually casts off its shell and appears in this part of the HR diagram, which is called a white dwarf. So in a brief moment of time, a few seconds, I described the evolutionary life of the sun that takes 10 billion years to be completed. So when you study HR diagram, you studied evolution of stars. You can pin down what changes the star goes through as the energetics of the star changes. What is the major byproduct of stellar evolution, which means why the stars are out there. So if somebody asks you this question a few months from now, so you study astronomy, I mean, what's the point of stars besides illuminating and give inspiration to poetry? Well, the stars are responsible for the production of atoms that make up our environment. You look at your body, you have iron in your body. You have iron in your bloodstream. You have calcium in your bones. You have magnesium. You have zinc. You have a carbon primarily. You have all kind of atoms in your body. Minerals. When you eat minerals, because you need to, you are pretty much eating a combination of several atoms, some of them containing exotic atoms that we better talk about. We breathe oxygen, basically. We breathe oxygen. So from where all these atoms came from? They came from stars that as they undergo these fusion reactions in their core, they produce these little tiny little bits of building blocks of nature. And when they are about to die, they release this gas enriched with the atoms they produced during their lifetime. They release this gas back to the interstellar medium that formed them. And then eventually new generation of stars picked on those newly formed atoms and incorporate them into their systems. So you could say that as the universe ages, as the galaxy becomes more metal rich. And then new generations of stars come in with more metals. So certainly if you think about life as dependent on certain type of chemistry, some people say, well, we could only exist now with our current set of DNAs because we had certain group of stars that populated the universe before us, and those stars produced the atoms that we now use to form our genetic code. So without those stars, we couldn't be here, basically. Life couldn't exist as we know. So what is the extra credit? That is a POP extra credit. It's going to be closing on Wednesday, so you have a couple of days to do, but those of you who are there, you can easily get it, is the following. So the star, in fact, you can go back to this application and review the question. So what type of stars are those close to us, our vicinity? You can find them here, the nearest star. So if you click on them, it's going to show that's the nearest star. So those stars that you could find if you have a spaceship, like in a sci-fi type of setting, you take a spaceship and then you visit all the stars in your vicinity. And then you go with a spectrometer, and then you go with not a thermometer, but go with a photometer. So we have a photometer and a spectrometer, the tools of astronomers we have been studying. And then you analyze the stars, and then you find their surface temperature, and you know how much energy they are sending out, so you know their luminosity. And then you place that information in this diagram, and you find that the majority of stars in our vicinity, they are main sequence. So look at this. Which means you could extrapolate that idea through the galactic disk. So if you are anywhere in the galactic disk, you visit a star system that is in the outskirts of our galaxy, but in the disk. So you set on that star, and then you visit their neighboring stars, right? And you do the same exercise, you would find some similar response. In other words, the majority of stars in our galaxy, especially in the disk, not in the galaxy, but in the disk, they are cool stars. That's what you're reading here. And that's the first question I'm asking my extra credit. What are the typical star in the galactic disk. They are cool stars, right? They are subluminous. They are not luminous at all. Look at this. They are 1/10 of the solar luminous, which means their sizes are small. So see, this is one solar radius, the size of the sun. They are smaller than the sun. So nature, when formed the stars, they are small, they are cool, and they are abundant, right? Abundant stars, 90% or more of the stars in the galactic disk, they are main sequence stars. They are of low mass, they are smaller than the sun, and they are cool. Now, let's change the exercise, and that goes to the second question in the extra credit. You go outside at night, and then you look up to the heavens, and then you see stars. Like here, in this Starry Night software. So you take the night sky, go to another time, let's say 10 o'clock. Now it's dark, and the Milky Way galaxy you can see nicely here. And then you have all these stars that you can see in the night sky, right? And then you ask this question, what type of stars those are that we can see so well? So, in fact, we do this exercise in our astronomy lab. What we do, we use a software and we go to any of the star and then we analyze and say, okay, this is a bright star, see that? It has an apparent magnitude, which you can see by reading in the upper left-hand corner. So, see, its apparent magnitude 2.71. Remember when we study magnitude, apparent magnitude, the lowest the number is, the brightest the star is. And we can't see stars fainter than magnitude 6. So magnitude 6 is the limit to it we can see. Magnitude 2, they are bright. So when you look at this bright star, look at the class of the star. They are class 2, which means they are giant. Look at, let's take a bright star. Is this a bright star? No, this is not a bright star. Juno is a probe. Okay, this is a bright star. Look at the spectral classification. Roman number 2 is a bright giant. Bright giant. So it's an evolve. How about this? What that is? Altair is a main sequence. That is a very bright star, but it's a main sequence. It's one of the stars in the main sequence we saw in the that is still main sequence. But if we keep repeating this exercise, not that one is a probe. This is a giant. See that? It's a giant star, magnitude almost 4. This is not bright at all. A giant, 2.75. So all the bright stars we see in the sky, and move around, see if you can find which star is this. Arcturus in Boötes. Arcturus is a giant. See that number Roman 3 K2 1 2 3 is a red giant. So it's not a main sequence. Another one here. Which one is this? Magnitude 3 doesn't give classification. How about this? It's a main sequence, Alkaid. It's a main sequence, but it's a B star. So it's a B star main sequence. So if you go to our HR diagram, a B star is somewhere here. Main sequence is up there, right? Is up there. Another one. The one we just, this one is a main sequence A2. Main sequence A2 is somewhere here. A2 is more like here. So basically, the stars that we see in the night sky, they are bright. They are bright because they happen to be luminous. They are up here in the HR diagram. And that's what I will do now. I'm going to probe only the brightest star in the sky. So the bright star in the sky, they populate. Some of them are main sequence, as you can see here. Some of them are giant. Some of them are supergiant. Okay. So basically, why they are seen in the sky? Well, they are seen in the sky because they are luminous. So they are luminous because they are, as we saw here, let's say the star like this one. Look how big they are. How about this one? Look how big they are compared with the sun. So where is the sun? The sun is somewhere here. So this little dot is the sun, probably here. So the sun is not. Where is the sun? The sun is here, maybe. Yeah, 5,800. That's the sun, right there. So stars that are up here in the HR diagram, you can see the size. They are enormous. Okay, 2 questions you have to answer. One, what are the characteristics of the near stars? And you can answer. They are what? If you look down here. They are main sequence, they are cool, and they are subliminous, and they are small. Let's give the characteristic right there. See that? So they are red, they are cool, that's why they are red, they are main sequence, and they are small. How about the stars? They are the brightest one in the sky, and we see a night sky. They are huge, they could be cold, or they could be hot, but they are luminous because they are big. Okay. So can we see? So those are the 2 questions. With respect to the nearest star, can we see the nearest stars? Well, not at all, because they are small. The luminosity is not that big, and then we miss them. We can't see a night sky. Okay. So with this, I give you an introduction to the evolutionary Hertzsprung-Russell diagram, and this diagram was found once a detailed information about the star energetic or the star energy output plus their surface temperature could be determined by astronomers. Now we have telescopes, we have spectroscopy being developed, we have photometry advanced, we have color filters coming in, and then astronomers could not only measure their surface temperature with very decent precision, but also they could use calculations and theoretical modeling to determine how large, how big the stars should be. Okay. So do you have any question on that one? All good? Oh, sorry, I was reading this. Oh, this is a spectrum. This is a spectrum of a star, a pre-main sequence star. I was playing with it, and we are trying to do some modeling here. By the way, I don't know if you guys are interested in the future become astronomers, or if you like to do some research in astronomy. If you are, talk to me. We have a group of science citizens, and we get together, we collect data from observatory, and we do fun things with it. Okay. So any question? No question? All right. Okay. So good night, everyone.